welcome to the second part of chapter 10. So this is going to be on resonance structures and molecular shapes. So we're going to build off what we were doing last time with drawing Lewis structures and kind of make those 3D. So instead of them being flat on a page, how would they look in real life, out in the real world, if we could see molecules? First topic is resonance structures. And so this is building on what we kind of stopped at the very end of the last lecture. So resonance structures are when you can write more than one correct Lewis structure for a particular molecule. And this usually happens when you have things with multiple bonds. So by multiple bonds, I mean things with double bonds or with triple bonds. This is really common with polyatomic ions. Usually if you can write, one structure, you can write more than one. So today we're going to look at how do we write these resonance structures and how do we recognize when you can write resonance structures. They consist of two or more electron dot formulas, right, or Lewis structures for the same arrangement of atoms. So it's the same atoms that are in the same kind of, the same central atom, the same peripheral atoms. All we are doing, we are just moving bonds. Do not move atoms, okay? Just moving bonds. And specifically, we're usually moving a double bond or a triple bond. And so we show that these are resonance structures with a double-headed arrow, and I'll show you that. And again, they're written by changing the location typically of a double bond. So you guys have heard of ozone, right? Out in the atmosphere, things like that. It's protecting us from those UV rays from the sun. And so ozone is a structure that we can write resonance structures for. So let's go about trying to do this. So the first thing you always want to do is to draw one Lewis structure, because you're not going to know otherwise whether you can draw a resonance structure or not until you start kind of going. So we're going to follow the exact same rules we were using to draw Lewis structures, and I'll show you how you can recognize that you're going to draw resonance structures. So it would only say, draw the Lewis structure for ozone. So we say, okay, so if we have ozone, we're going to put our 3 oxygens. I'm just going to kind of put them in a line. Okay, and then we figure out how many electrons we have total for this structure. So we have, 3 oxygens, and each of those oxygens have 6 valence electrons. So we have 18 electrons we can use in our structure. So we're going to use 4 of them, making those first bonds. So we have 14 electrons left. So we can go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so if we look at this, the oxygen on the left and the oxygen on the right have complete octets. They have 8 valence electrons around them. But the oxygen in the middle only has 6 valence electrons. It has, 2 from each of the bonds, so that's 4 total, and then 2 in that lone pair, so it has 6. And again, the way that we, we're talking about solving this issue was that we can say, okay, one of the oxygens on the edge, can donate its electrons, and form another bond. It can form a double bond. So here's where you recognize that this can be drawn, that this has resonance structures, because it doesn't matter right now which oxygen I pick. This oxygen could donate its electrons, right? And we would draw this structure. Right, so that, that structure, when that oxygen donates, its electrons, makes another bond so that all of the oxygens have 8 valence electrons, that is a correct Lewis structure. But we could just as easily have had the oxygen on the right donate its electrons, and that would have formed this structure. Okay. So both of these structures are correct, right? And it just depended on which oxygen did we pick, right? And so that's how you'll recognize that you can draw resonance structures. So these two ones that I've drawn at the bottom, and I'm going to show that they are resonance structures with a double-headed arrow. These two structures are both correct Lewis structures for ozone. So it just depended on which oxygen chose to make the double bond. So both of them are correct. And so when it says, draw all of the resonance structures, it's asking you to draw all of the possible correct Lewis structures that you can. Again, you're not moving the oxygens around, right? I didn't change how they were arranged. I didn't move them. The only thing I'm doing is moving the location of the double bond. So here it's on, it's going to the left oxygen, and here it's going to the right oxygen. So that's the only thing that's different. So these are resonance structures. Let's try another one. Let's draw resonance structures for SO2. Okay, so following, if we thought about following our hunk rule to figure out which one goes in the middle, you would realize, okay, well, oxygen and sulfur are stacked on top of each other. So how do I know which one goes in the middle? So this is where the one that's, the least electronegative will go in the middle. That would be sulfur if you looked at a table of electronegativities. But another, good way to think about this, is the one farthest from fluorine, or if you get into a situation like this, kind of a pro tip, see how there's only one sulfur and there's two oxygens? Usually that means the sulfur is going to be the one in the middle. A lot of times molecules are symmetrical. So anyway, regardless, we're going to put sulfur in the middle here. So sulfur is going to go in the middle, and we're going to put our two oxygens on either side. And then we figure out how many electrons we have to work with. So we have sulfur plus two oxygens. So sulfur has, equals, sulfur has 6 valence electrons plus 2 times 6 for each of those oxygens, so we get 18 electrons. We're going to bond the oxygens to the sulfur, just like that. So we subtract out 4, so we have 14 electrons left. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we're done. So the oxygens have complete octets, but the sulfur only has 6 electrons right now. So if you're, thinking ahead, this looks very similar to our structure for ozone, right? It's almost identical. The only thing that's different is that there's just sulfur in the middle instead of that oxygen. So again, we need one of our oxygens to donate some electrons and make a double bond, right? So instead of it having that lone pair, it's going to move them, make a double bond. But again, it doesn't matter which oxygen we pick. We could pick the one on the left, or we could pick the one on the right. So this is telling us that we can draw 2 different resonance structures for this molecule. One resonance structure where the oxygen on the left is donating its electrons, and the other resonance structure where the oxygen on the right is donating its electrons. So we'll do the one on the left first. So here's our one resonance structure. And then we could have done, the one on the right instead. So then it would look like this. So those are both correct resonance structures for sulfur dioxide. These are both correct Lewis structures. And again, make sure you're always separating them with a double-headed arrow in the middle. That is a symbol in chemistry that tells you that these are resonance structures. These are both correct Lewis structures for sulfur dioxide. So again, always start off, just draw the Lewis structure normally and see when you get to this step and you're like, I need one of my oxygens to donate its electrons. Then you're like, okay, now how many times, how many different ways could I have done that? So that's the stuff on resonance structures. So go ahead, find your lecture worksheet, do problem 12. Problem 12 will get you some practice with drawing resonance structures. And before you go on to the next part of this lecture, you need to be really, really solid at drawing Lewis structures because, Lewis structures are like the foundation for chapter 10. Everything we do in chapter 10 is based on you drawing your correct Lewis structure. So make sure you're getting really good at those. You've put in the work, you've done the practice, and of course, always ask me questions. So pause here, do number 12, and then come back and watch the rest of the lecture. All right. So now we've gotten really good at drawing Lewis structures. We've learned about how to draw resonance structures. So we're going to talk about this topic called VESPER. So VESPER is an acronym. It stands for Valence Shell Electron Pair Repulsion Theory. And all it really means is that molecules are not flat, right? Like out, in the real world, molecules don't just lay flat on the paper. They don't look like the Lewis structures we draw because the world's not completely flat, right? Instead, molecules have 3D shapes, and they have these 3D shapes because electrons repel each other. So rather than laying, flat in the page, the electrons kind of spread out, and when they spread out like that, they make three-dimensional shapes. And so we can figure out, we have names for these shapes, and the way that we're going to figure out what the shape is we're going to draw the Lewis structure. That is always step one. So like I was saying earlier, if you can't draw the correct Lewis structure, none of this is going to be right. So make sure you are getting really good at drawing Lewis structures. And then we are going to count the number of electron groups around the central atom. So this includes bonds. Bonds count as an electron group, and lone pairs count as electron groups. So it's just areas of electrons, essentially, and it's around the central atom. We don't care what the atoms on the edges are doing. We don't care about their bonds. We only care how many electron groups are around the central atom, how many bonds, how many lone pairs. And so what happens, like I said, in reality, is the electron groups end up being as far apart as they possibly can. Because electrons are negative, and so if they come too close to another electron, they'll repel. And so the way they account for this is that they spread out and they'll be as far apart as possible. And so this whole theory is called VESPER. So the shape of the molecule is determined by two things: the number of electron groups surrounding the central atom and the number of atoms bonded to the central atom. So we're going to go through and see all the different shapes that your molecules can have. So if there are two electron groups, okay, and so by electron groups, I want you to look at carbon dioxide here. This counts as one group of electrons. Remember, we're only looking at carbon. We're only looking at the central atom. So on the left side of the carbon, there is double bond, right? Even though the double bond is made up of 4 electrons or of 2 bonds, it's just one area of electrons. Okay, so this is counting as one area of electrons. This is counting as another area of electrons. So that's where we're getting this two electron groups. One double bond on the left, one double bond on the right, for a total of 2 electron groups. So anytime you have 2 electron groups, this will have a linear shape. Okay, linear electron geometry, and then the bond angle is going to be 180 degrees. You are going to be responsible for knowing the shapes. So you're going to be responsible for being able to recognize, like, okay, this has 2 electron groups, and you're going to memorize anything that has 2 electron groups has a linear shape, and linear shapes have a bond angle of 180 degrees. So those are what I want you to know. We are not going to do tons and tons and tons of different shapes. You can learn more about those in Chem 20, or if you take more chemistry, but we are going to learn some to help you out when you get there. So you do need to know 2 electron groups is linear, which is a bond angle of 180 degrees. And if you look, actually, if you have your lecture worksheet right in front of you, there's a table right at the beginning of the VESPER page, and it shows all the things you need to know, okay? So I would maybe have that out while you're going through the rest of these slides, and so that you can reference it and see that table. It's table 10.5 in your textbook if you don't have the lecture worksheet in front of you and you have the textbook. All right, moving forward, 3 electron groups. Okay, so again, we are just looking at the central atom, and so we are looking at things with 3 electron groups. So like this, this structure here, or this one, this might be how we draw the Lewis structure, right? The one on the left, you would put carbon in the middle, and you would come up with the fact that it's double bonded to oxygen and single bonded to each of the hydrogens. So there are 3 electron groups, 1, 2, 3. Again, the double bond is only counting as one electron group, even though there's 2 bonds and 4 electrons and all that stuff. It's only one area of electrons. So you're just counting area of electrons around that carbon. And so the way that the Lewis structure is drawn, these are at 90-degree angles, right? And then this is at 180 degrees. And so in reality, the molecule again wants to spread out as much as it can. So what happens is that these electrons push these hydrogens down. It pushes the hydrogens down until they are getting equally spaced, and it looks like this one in the middle. This is what it's actually going to look like, where this is 120 degrees, this is 120 degrees, this is 120 degrees, and they are equally spaced around that central atom. Okay, so this shape is called trigonal planar. That's how you pronounce it, not trigonal. It's trigonal planar, and it has a bond angle of 120 degrees. So again, you're going to memorize, okay, if it has 3 things bonded to the central atom, it's trigonal planar, bond angles are 120. Okay, but again, if you don't draw the Lewis structure right, then you're never going to get the rest of it. So make sure you're practicing your Lewis structures. So this one is related. This is like a subset of trigonal planar. Okay, so there are 3 areas of electrons around the sulfur. So again, we're looking at the sulfur. Okay, so there's 1, 2, 3 areas of electrons around the sulfur. But this isn't trigonal planar. This has trigonal planar electron geometry, which we're not going to really mess with. I want the shapes. Okay, so this is trigonal planar electron geometry, but the shape is different, because if we look at what the molecule actually looks like, when we have the actual molecule, the electrons don't show up. The electrons aren't just like sitting up here. Instead, the electrons, because they are still repelling the electrons in the bond, the electrons have pushed these electrons and those bonds down so that it still gets this shape where they're bent, but the electrons don't show up. Okay, so what I want you to know here is that, okay, if it has 2 bonds and 1 lone pair on the central atom, right, like this, just like this, if it has 2 bonds and 1 lone pair, that means it's bent and it has a bond angle of 120. Okay, so like I said, this is a subset of trigonal planar, but it's different because in trigonal planar, there's 3 things bonded to the central atom. In bent, there is 2 things bonded to the central atom and 1 lone pair. Okay, but the bond angle is the same, 120, 120. Again, if you're looking at the lecture worksheet, this will really help you out. It also has all of these examples on there. It's like a good summary sheet. All right, so we've done 2 electron groups. We've done 3 electron groups. Now let's go to 4 electron groups, and that's the most we're going to do. We're not going to do anything else. So 4 electron groups. So here, this is methane, carbon tetrahydride, and there are 4 things bonded to the central atom, right? 1, 2, 3, 4. We have 4 bonds going to the central atom. When you have 4 atoms bonded to the central atom, then we call this tetrahedral. Okay, and tetrahedral has a bond angle of 109. It's actually 109.5, but 109 will do for this class. And again, so if you look at what it looks like, this is now starting to be 3D. Right, one of the atoms is coming, into the page. One of them's going, out of the page. One of them's going into the page, and we have this 3D molecule shape. And the reason is because, right, these atoms, these electrons want to spread out as much as they can. They want to maximize their space, and so the way that they do that is they pop out of the page, and they're now 3D. So when we have 4 atoms bonded to the central atom, this is going to be tetrahedral. 109.5. So this is a subset. So like tetrahedral is kind of the overarching group, right? 4 things around the central atom. So this is still 4 things around the central atom, right? 1, 2, 3, 4. But now, instead of having 4 bonds, one of those bonds has been replaced with a lone pair. So this is when we have 3 single bonds and 1 lone pair, okay? So this is still tetrahedral, what we call electron group geometry, because there's 4 areas of electrons. But again, I want us to know the shape. So this is what I want you to know. I want you to know that the shape is trigonal pyramidal, okay? Because look, it looks like a pyramid, right? So trigonal pyramidal is how you say that. And the bond angle is still the same, right? It's still 109.5 or 109, but the name of the shape is the same, because if you look, this, right, this shape, this is tetrahedral. We have 4 things bonded to the central atom. Here, this shape, right, this top one, these electrons, they don't take up, that we don't see them in the molecule. And so this is what I'm actually looking for. This is a trigonal pyramidal shape, because again, looks like a pyramid. Okay, looks like a triangular pyramid. So that's why it's called that. Okay, but the bond angle is the same. You just need to know the different shape name. I would recommend start making flashcards for all of these. Our last one that we're going to talk about is still, there's 4 areas of electron density, right? 1, 2, 3, 4. But now 2 of them are bonds and 2 of them are electrons. Okay, so this actually has the same name as a previous shape. This is a bent shape again. This is a different type of bent. Before, that was when we had 2 things bonded to the central atom and 1 lone pair. Here, we still have 2 things bonded to the central atom, but we have 2 lone pairs. We're still going to call this bent, which I know is confusing, but they do have different bond angles, okay? So this will have 109 because there are 4 areas of electron density. So anytime you have 4 areas of electron density, it's always 109. Anytime you have 3 areas of electron density, it's always 120. And then 2 areas of electron density, it's 180. The thing that's changing is the name of the shape. Okay, so again, I would make some flashcards. So this is called bent because, it looks like bent. This is why, if you'll remember in the previous lecture, I told you be very careful how you draw water. And I told you don't draw water, right? Or don't, when you're doing electrons, we think about how we would do the electron dots for oxygen. That would be how it would go. And so it would make bonds to hydrogen like this. This is why water has a bent shape. Okay, so you need to be very careful that you don't draw water like this. Because this would make water look like it's linear, all right? It looks like they're all lined up. And when we get a little bit farther in chapter 10, this would make you believe all kinds of things of water, or all kinds of things about water that are not true. So be very, very careful. Don't ever do that. Like, don't ever, ever, ever in your whole life ever do that. Water should always be drawn in a bent shape, because then you will know lots of things about water. Again, more on that later. So let's see how we might use that. So this says, use Vesper theory to predict the shape of silicon tetrachloride. So the first thing you would always do is draw the Lewis structure. So it's drawn down here. I'm going to still go through and draw it just kind of how how we've been talking about doing it. So our first thing, we would look at the honk rule. Right? Silicon falls directly under carbon. So silicon makes 4 bonds. Chlorine is a halogen, which means it, goes here. It can only make 1 bond. So we put silicon in the middle because it can make the most bonds. So silicon in the middle, and then we put our chlorines around the outside. Okay, and then we add up how many electrons we have to work with. So we go silicon plus 4 chlorines. So we have 4 plus 4 times 7. So we get 28 plus 4 gives us 32 electrons. So then we're going to bond all of our chlorines to our central atom. 2, 4, 6, 8. So we're going to subtract out 8, which gets us 24. And now we go through and we finish our octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Double check, make sure everything, has its octet, which it does, right? Each of the chlorines has 8 around it, and the silicon has 4 bonds going to it, which means it has 8 electrons because each of those bonds has 2 electrons in it. So this is a good Lewis structure. We're done drawing that. So the first step is to always draw the Lewis structure. And then our next step will be, okay, let's think about all of those, shapes that we just learned. How many areas are around the silicon? Remember, we're just looking at the silicon. So silicon has 4 bonds going to it. 1, 2, 3, 4. Right? So that's 4 areas of electron density. So that means it's going to be tetrahedral or some subset of tetrahedral. Since all of these are bonds, none of them are lone pairs, we don't need to think about the subsets. The subsets are only when they start being replaced. So this is going to be a tetrahedral shape. And anytime you have tetrahedral, this is going to be a bond angle of 109 degrees. This, you're just going to have to start memorizing. You need to make flashcards. So the people that, that are math heavy people, you guys loved chapter 9 and chapter 7 and all of that stuff. If you're not a math heavy person and you're like, man, I would way rather memorize stuff, this is the chapter for you. This is the memorizing chapter that has no math. Or very little math. So go through, like I said, start making flashcards for these. Look at that table 10.5 in your textbook or on your lecture worksheet. That's the stuff you need to know. You don't need to know really the electron group geometry unless that's going to help you memorize, the bond angles. But you do need to know the shapes. The shapes is big. The bond angles is big. So go on your lecture worksheet now and do problem 13. Again, right above problem 13 is going to be that table 10.5 that's got all the, the summaries. Use that to help you and start working on memorizing that.